Hello everybody, my name is Chaimae Zedak. I'm a PhD student in the National Higher School of Electricity and Mechanics. Today, I'm going to be talking about my research paper entitled Photovoltaic and Battery Systems Control and Monitoring for Energy Management using IoT. Before coming up into the proposed solution, let me begin with the problematic statement of this topic. As being the network linked directly to the final consumer, the electrical distribution network comes into contact with several devices, forms of energy, equipment, and their corresponding variable and unpredictable behavior. The interaction with these different equipments makes the management of this network a difficult task. Energy management in distribution networks requires a large amount of data in order to make decisions in a brief time. The solution is to equip devices with IoT technologies and take advantage of new information technology for the interest of the network. These technologies meet and impose several and significant challenges, namely security, interoperability, reliability, and scalability. These challenges must be overcome to encourage the use of IoT in electrical networks. There are several specified application protocols for the distribution of data packets, such as OPC-UA, CoAP, MQTT, AMQP, etc. In this research paper, we chose the MQTT as being a particularly interesting and attractive protocol for M2M applications. This protocol uses less data to send a message in a short time and is considered very optimal in terms of energy consumption. It can also interfere with a large number of objects as a lightweight publish-subscribe M2M communication protocol. For reliable transmission, MQTT defines 3 levels of quality of service, and for security, it provides TLS-SSL security mechanism. The general concept of the proposed architecture for smart grids is to exchange data between the MQTT broker and the various equipments which are MQTT clients using a secure M2M communication. To collect data from sensors installed in the field, each system will be connected to a Raspberry Pi through sensors to route data to the broker. Communication is established in both directions, from the grid to the EMS to collect data, process it, and display it on the system. In this case, all Raspberry Pis will publish data remotely to the broker under the name of different topics, and the EMS will subscribe to the broker to display it. In the opposite direction, the EMS can also publish opening and closing orders to the broker in order to control the availability of generation units. The Raspberry Pi in this case will subscribe to the broker to execute instructions. The use of encrypted M2M communication network with protocols meeting the security requirements and the CIA triad is the appropriate way to improve the security of the electrical infrastructure. To test the solution, a small photovoltaic installation made up of a photovoltaic panel and a lead battery has been considered. The sensors used are digital energy meters, which communicate via the industrial Modbus RTU protocol with the Raspberry Pi through USB RS485 converter. The Raspberry Pi is considered here as a Modbus MQTT gateway to ensure interoperability between the two protocols. To communicate data to the broker, an M2M gateway has been used with 4G connectivity as a VPN concentrator requiring a static and public IP address since the data is routed through the public internet. To secure data from end to end, a VPN tunnel has been created using OpenVPN by data encryption. OpenVPN generates RSA certificates, and only a client having the certificate can establish communication with concentrator. The publish-subscribe flow is presented in the following figure. Sensors will collect the voltage, current, power, and energy from the inverter linked to the PV and from the battery, in addition to frequency, power factor, and temperature humidity. Each measurement will be communicated under the name of different topics. Once routed, the data will be stored and displayed locally on the Raspberry Pi as shown in the following figures. And then it will be displayed remotely on a human-machine interface developed under Python, as you can see. Now back to the electricity grid. The collected data will be used to estimate the parameters of energy sources and the state of charge of the battery systems. The estimated values will be then used as inputs to the energy management algorithm, which will generate the appropriate actions for all energy sources. As a conclusion, we can say that the proposed solution is a low-cost solution that respects the major reliability, security, and interoperability challenges with flexibility to introduce new objects to be connected to the system. That, ladies and gentlemen, was what I wanted to share with you during this presentation. Thank you.